Okay, so the plan for today is just to go over the main introduction for the course. Let me see. Class will always start at the 10 past mark, so please try to be on time so you don't miss anything important. And apologies there for changing the the hour when I first shared my screen. It said 10 past 10 instead of 11. Right. So the main plan is there are 6 problem sets that you can solve roughly every 2 weeks, and the lowest mark is dropped. And for that reason, there is no way to make up for a missed problem set. There's also no late submissions, so please try to keep that in mind and build that into your planning and how you schedule solving these. There are also weekly quizzes, and I will give you an example of such a quiz today. The lowest 2 quizzes are dropped, so there's 12 weeks of class, so only 10 of them will count. The quizzes will be mostly graded based on submission or maybe like some multiple choice. Now, I don't like to keep track of attendance or anything like that. I don't even really like the idea of the quizzes too much, but I think it's important for me to try to keep the class engaged and attending the online lectures. Yeah, given that I will be recording these, a lot of you might be tempted to just watch the recording at like twice the speed or something, and I guess that's fine as well. But do keep in mind that the quizzes I will be usually giving the question during the lecture, and you have to submit it within a few hours. Like I said, I will give you an example now. Okay, so Math 246 is a bit of an odd course. It's meant to be an introduction to proofs, and also I will try to make this an invitation to learning more abstract math, since I believe I will try to convince you that learning abstract math can make learning concrete math easier and make some very even applicable concepts much easier to grasp if you go one level above in abstraction. And I will try to give you very concrete examples of this. Maybe not today, maybe not this week, but hopefully as the course moves on. This course is usually like a form students take this course to bridge the gap between courses that are not necessarily proof-based and maybe some more advanced courses like 337 that rely heavily on writing and understanding proofs. And it is also a great excuse for us to learn some topics that don't usually get a lot of attention or any at all in other courses. So it is my hope that if you already know how to write proofs and already know about these subjects, then you will also hopefully find something interesting in the course by learning um, material that you are unlikely to encounter anywhere else, uh, unless you take like a very specific course on that topic. And I will share with you the syllabus so you can actually know what I'm talking about. And in the meantime, let me see, just one second. Right. If you have any questions, this is a rather larger group. Feel free to paste them in the chat. I try to keep track of that. You can also just unmute yourself and interrupt me. I don't mind that at all. So this is the syllabus that it posted on Quarkus right now. The contact information is there. Also, how to sign up for Piazza for discussions and questions, and Gradescope for submitting the problem sets. This is, I think, just a click, so it should be fairly straightforward for everyone. There is a part of the rubric that evaluates communication. Don't take this too seriously. You don't really need these points to get a perfect mark in the course. But you can get some extra points that might help you out in the final or for the problem sets. And the idea is that I don't know if you've taken this course before or not, but I taught it last term, the term that just ended for the winter term, and there was a bit of chaos and confusion sometimes. So I want to mitigate that, and for that I implemented this clear communication, right? So if you're going to write an email with a question, please make sure that the question is not already answered here or maybe someone already asked it on Piazza. If you do answer things on Piazza, it doesn't have to be correct. That's not the point of learning. This is not a punitive thing, right? But the please try to be clear. Try try to be clear. Okay, so I think I talked a little bit about the course description of philosophy. Oh, there's also a final exam. That one is the only activity that will be in person, and that is not up to me, that's up to the department. And it will be somewhere late August, I believe. And it's worth quite a bit. But if you read this, my idea is that students who solved the problem sets on their own and put in the work and attended the lectures and try to understand the course material shouldn't find anything too surprising in the final. That's what I think evaluations should be like. I already mentioned the short quizzes. I think I already mentioned communication, mostly 6 problem sets, lowest one is dropped. There's a lot of details here you can look at. Here's the actual distribution of marks in case you're interested. As you see, the final is worth quite a bit, but there will be plenty of time for us to prepare for it. Okay. So here are the actual subjects that we'll be covering. So the first one, okay, let's see. Yes, that's correct. The total mark adds up to more than 100. Like I said, if you look at the communication, that's the 5 extra points you get. So you could completely neglect that and still get a perfect mark in this course. Yes, that's a good observation. Oh, and that's another reason why there's no late submissions or way to make up for the problem sets, right? You could get more than 100 by adding up these points. So that's that. Now, of course, if you do have an emergency or something, feel free to email me. It's not like I think we all have common sense, right? So don't be mortified by this. The first topic is foundations. So we're going to talk a little bit about set theory, and we're not going to really cover logic as a subject itself, but we're going to use logic to develop some basic proven techniques, and we will grow this into more advanced techniques as the course moves on. The most important aspect of the natural numbers is, of course, induction and well ordering, and we will cover this in the first 2 weeks. Every chapter is divided into, I think, almost perfectly 2 weeks. There might be a little bit of overflow here and there, but that's mostly the case. Okay, I think I've mentioned everything so far. The recordings. I will be posting lectures for the notes that I'm writing during class. If these have typos or anything, then please let me know either via email or you can just post it on Piazza. And this counts as communication points. Basically, anything that helps reduce the chaos in the course will count as communication points. So then we will look at the integers. If you've taken this course before, then this might seem more or less familiar. It's basic number theory, elementary number theory. Now, we will also talk a little bit about fields and constructions. If you took this course with me before, we didn't really see any constructions, at least not in detail, of the integers or the rationals or even the reals. And last term, we constructed, quote unquote, constructed the real using dedicant cuts. This time we will do it using a completely different technique, which is called Cauchy sequences, in case you want to contrast that with last term. We will also talk a little bit about more advanced set theory because it is very useful as a proven technique for other courses, even if you don't care about set theory. Now, basic point set topology is also something that I find quite interesting, and it blends nicely into this sort of bridging between the courses. Many of you have taken some sort of linear algebra, but you haven't taken any analysis, but you might be interested in taking real analysis in the future, and this is a good excuse to connect those two. Now, I think I didn't mention this, but so my field of research is set theory and combinatorics with some connections to theoretical computer science. For that reason, I want to add some combinatorics in the course. This is the last chapter. Now, I kind of want to give students the freedom to choose exactly what they want to focus on. And of course, this will depend on what things you found interesting during the course, what things you didn't find interesting. Maybe we can find a subject that is for sure not mentioned anywhere else, like something really specific, really niche. And I think you could all benefit from that because well, hopefully you find it interesting. Tutorials start this week, so in a few hours, the Jake's tutorial will take place. So make sure you attend that. See the schedule. We all have the same Zoom link. Here's the course calendar. There are some holidays and weeks on which there are no tutorials, so please keep that in mind. And I think that's pretty much it. Okay, so I will give you a few minutes to think about whether you have questions about the syllabus or not. And I try to keep logistics to a minimum. Okay, so question Helen asked, do we have any textbook? So for the first chapter, I will just be posting the notes since these will be mostly self-contained. But for other chapters, I may give you reference to a textbook uh, as a complementary material. But as I promised, I don't know if somewhere in the syllabus, maybe I wrote it. My notes will be self-contained, so you should be able to understand and solve everything, including the final and the problem sets, just by reading the notes. So we are not really following a textbook per se. Yes, you're welcome. Let me go back to the other screen. Okay, so I think maybe let me add some words on how to learn math in general. In my experience, the one factor that determines whether a person is successful or not at math is mostly the number of problems that they've solved, right? And you can draw many analogies with this. It's a bit like working out. If you if you lift weights that don't really challenge you, then it might help you keep in shape, but you're not going to get any stronger. You actually have to feel the burn a little bit, struggle a little bit to actually become faster or stronger, if you want to follow this athletic analogy. And same thing happens in math. Now, a very important component of this course is learning how to read and write clearly. And to learn how to write proofs, you need to write a lot of proofs. But there is another aspect that we will also cover in this course, not only writing proofs, but also solving problems. And these two are slightly different things because one emphasizes clarity in communication, and the other one just emphasizes, can you find the solution? Can you decide if this is true or not? And regarding the second one, sometimes it happens that you're given a long list of problems that you kind of already know how to solve. Maybe you just haven't figured out how to write it. Those problems are good practice to writing proofs, but they might not be good practice to learning how to solve problems. If you already know, if you have an idea on how to do it, the problems that will actually make you grow are the ones where you struggle. The ones where you read the prompt and you say, okay, I have no idea how to prove this, or I have no idea why this should even be true. And then there's this weird stage in which you first have to convince yourself that what you're trying to prove is true, or that what you're trying to achieve is solvable in the first place. And then you sort of break down the problems into smaller chunks and then solve them individually, and then maybe find a clever way to merge those partial solutions together. I know what I'm saying sounds very abstract because, of course, there's no one formula that will solve all problems, but we will hopefully illustrate this general mindset during the course. And let me think, what else can I say about that? If you're reading a textbook that is mostly mathematical, then my suggestion for that would be that whenever you encounter a definition, you try to come up with some examples and some non-examples yourself for that. And whenever you encounter a theorem, most textbooks that are pure math are theorem, definition, right? When you encounter a theorem, try to read and understand the statement on your own, and then read the first sentence of the proof and try to prove it yourself. And if you get stuck, then read the next sentence and take that as a hint. That is, of course, a lot of work, but if you put in those extra hours, you will understand the material better than if you just skim through it, memorize the theorem, and maybe don't even bother understanding the proof. Now, of course, it helps having someone to give you feedback on your work and someone to guide you through maybe some of the more confusing passages of the material. Not all textbooks are written as clearly as we could hope. Okay, I think I've ranted long enough. Do you have any questions about the syllabus? I think I've covered everything regarding syllabus and logistics, so we can actually start the actual course in a few minutes. Now, I did promise I would give you one example of quiz, so let me scroll down. So here's the very first definition that we will be looking at for the course. So the power set of a set X, which we denote by calligraphic P of X, is the family of all subsets of X. You can find that in symbols. Practice problems. Okay, so the question is, are we going to get practice problems of any sort? For the final, yes, I will give you a list of practice problems that you might expect be more or less similar for the final. Now, the problem sets, you already have access to the first problem set on Quarkus. There are 7 questions that you need to submit to get full marks on that problem set, but I believe there's anywhere between maybe 14, 15 questions in total. And it should be clearly marked, clearly indicated which ones will be marked and which ones will not be marked. Basically, the ones that aren't worth any points will not be marked. Those are all practice problems. Oh yes, sorry, I was going to paste the link. Those are all practice problems. And I'm happy to refer you to more practice problems if you want. But yeah, there will be plenty of practice problems. Yes, you're welcome. Also, the tutorials are also important, so make sure you attend those. Those are an excellent opportunity for you to ask questions. All of those are just practice problems, right? Okay. Now, yes, all the notes will be posted on Quarkus as a PDF and also the recordings. Now, the recordings are a bit of a bonus. So if something goes wrong on my end in a technical sense, maybe I forget to record or the recording gets lost for whatever reason, I will not really make up for this by remaking the recording on my own. I will, however, try to keep the notes clear, but the verbal aspect of the notes as I'm writing them is also quite important, right? The order in which I do things is important. So please make sure you attend the lectures. There's a clear correlation between students who regularly attend the lectures and those who do well on the tests, regardless of other factors, right? So keep that in mind. Right. So while you answer the quiz, I can write down some examples that we will look at. Actually, let me just give you one example. So what would be the power set of the empty set? We will know the questions for the day's quiz during the lecture, Monday or Thursday. Okay, so the idea is every week there will be a quiz, but it will not always be the same day. It might be Monday or it might be Thursday. And I will give you time during the lecture to answer the quiz as I am doing now. But the idea is that I will define a concept, give an example during the lecture, and then the quiz will be something that will be easily solved with what I just explained. And you don't have to actually attend the lecture to see the quiz. I will post it on Quarkus anyway, but it will make a lot more sense if you're actually attending the lectures. Also, there's a delay between me finishing the lecture and uploading the recording, and that delay might be bigger than the time you have to submit the quiz. So I hope that answers the question. But yeah, the plan is that every day before the lecture, I will post the quiz on Quarkus. Sometimes Monday, sometimes Thursday, but it will be exactly one every week. Okay, so while you answer this, let me see if I'm getting any more responses. Okay, great. Looks like I did recognize some of your names. Not all of you from Mat 246. I think I have T8 some of you as well. Okay. Yes, okay, so Ray answered the question for the first example. Now, usually when I make these quizzes, I will of course try to give you enough time to absorb the definition. Right now, I just wrote the definition and gave you the quiz, but I think that's fine. Right. So the power set of the empty set is the family of subsets of the empty set, right? So which sets are subsets of the empty set? Well, just the empty set itself. We will write these operations in more detail on Thursday, but you do need this definition for the tutorial, which is why it's the first one that I'm covering. Okay, let's say 2 more minutes. 2 more minutes to answer the quiz. Don't worry too much about correctness right now. Like I said, I didn't really give any examples. Do the class quizzes have a time limit? Yes, they have a deadline, which will be 3 hours after the lecture is over. Right now, this quiz is a bit longer, but usually it will just be one question, and it will be one question that you can easily answer within a few minutes just by having attended the lecture, right? The quiz is not really supposed to be like a challenge or anything like that. Okay, 1 more minute. There's still some people answering the quiz. So like I said, this quiz is a little bit longer. Usually you can answer this within 1 minute and it should just be one quick question. Like the only math question in the quiz. That's something that you might expect. Okay, there are still some people answering the poll, but in the meantime, let me answer the question. So the mark about this in-class quiz, yes, I will try to give the marks as quickly as possible, probably within the same week that the quiz took place, so that you can keep track of all your grades. The name, okay, someone asked me if I could give the name of the textbook that could be handy at some point. Yes, as soon as we cover something that will be mentioned in some textbook, I will give you the names of the textbook so you can find them. And yes, there is a tutorial later today. I think it's like what, an hour after my class ends. So yes, tutorial starts this week. Okay, sorry about that. I hope you cannot hear. There's a bit of noise. I think someone's mowing the lawn here or something like that. Should just be a few seconds. Okay, well, thank you all for answering the quiz. In the meantime, let me write some more examples, right? So the power set, the family of all subset of X. So what are all the subsets of the empty set? Well, every set is a subset of itself. So the empty set must be contained in the power set of anything, right? So actually, the empty set is an element of every power set. And that already tells you that the power set can never be empty. So don't worry if you didn't write the correct the correct answer. This quiz was mostly just an example, right? Okay, so maybe let's do one more. So what if you take a set that is no longer empty, like the set containing the empty set? That one has an element, which is the empty set, right? So what would be the power set of this set? And as you can see, I can keep doing this, getting bigger and bigger and more complicated sets. So what do you think this should be? I already know that when I start listing out the subsets of any set, I have to start with the empty set, because the empty set is a subset of any set. So the very first element will always be this one. But this time, this set is not empty. So of course it must have more subsets, in particular itself, right? Itself is a subset, which is different from the empty set, right? And there you go. Now, like I said, we will write some more definitions in more detail next class. This is mostly just to illustrate maybe the style of the lectures. Okay, so here's one concept that you're also going to need for the tutorial, which again, we will cover in more detail. Here's a definition. So if A, B are sets, then A cross B is the set of all pairs of elements where the first coordinate is in A and the second coordinate is in B. And I'm sure you've seen this in some class, either calculus or linear algebra. I'm sure you've seen this. Now, something worth keeping in mind, and I will add these comments in green, we are not, so in this class, I'm not going to define this symbol to you, but you can figure out everything that you need to know about this symbol by knowing how to compare pairs, basically. But all you need to know, all we need is two pairs of elements, A, B, are equal if and only if, it's a bit too thick. If and only if, and let me just add a little def to denote that this if and only if is by definition, right? It is not a consequence. It is not something you can prove. It is literally what I'm using to define this symbol. So two pairs are equal if and only if they are equal coordinate-wise, right? So the first coordinates match and the second coordinates match. And that's all you need to know. There is a way to define this symbol in a more axiomatic, abstract, set theoretical way. We're not going to need that. So this is all we need, and this is everything there is to know about tuples or pairs is what I just wrote down in green. Okay, so the next definition that I want to cover is that a subset of A cross B is called a relation. So how does this make sense? Maybe let's look at an example. So we have two sets. Typically, relations will mostly be defined on the same set. That means something of the form A cross A, but they don't have to be the same set. And one particular type of relations that are very important to us are called functions. And functions are usually defined between different sets. Let me give you an example of a relation. So let's see. Let's start with a very concrete example. So let's say that A is the set of students of this class. 2, 4, 6. Right? Then let's say R is a subset of A cross A. And let's say that R consists, I'm going to make up names. I don't really I don't really want to use real names. So if this is by pure chance a real name, then it's not intentional. So something that I can do is I can form a pair with Alice and Bob, right? And maybe this relation is symmetric, so I can also invert these. Bob and Alice are also related. That doesn't always have to be the case, right? So maybe Alice is related to Charlie somehow, but not the other way around, and so on. So this is already an example of a relation. It's a relation that's relating Alice to Bob and in reverse, and Alice to Charlie, right? So one way to think about relations is that they are connecting different things by an arrow, something like that. So Alice, Charlie. So for example, Alice is pointing in these two directions and Bob's arrow is reversible. Now there are many types of relations, and these will tell us a lot of things about more abstract math. We will use this concept a lot. Okay, so here's one piece of notation that you will find useful. So notation, if R is a relation on A, meaning that R is a subset of A cross A, right? That's what it means to be a relation on a set. It means that it's a relation on A cross A. Then we denote the statement A comma B being an element of R, which it may or may not be. We denote this fact simply by this symbol, right? We put R in the middle. And I'm pretty sure you've seen this. You've seen this plenty of times. You use this sort of notation for things like addition and multiplication and other things. This is the same idea, although in those cases, those are operations, and this is just a relation, right? So, okay, let's look at an example, another example. So let's say A is related to B, students. Okay, let's do the previous example. Let's say for students A and B in the set A that I defined earlier, we define this relation A related to B if they start, if their names start with the same letter, right? So this is a relation on students in which I basically tell you, you have to get in a group with all students whose names start with the same letter. Let's say the first name. Now, what type of relation is this? And we can look at this relation. And by the way, if you want to find a more abstract example, you can find one in the first problem set, because what I'm doing here is I'm defining a function from the set of functions to the set of letters. And I'm saying if, okay, so the function is defined as follows. Every student gets assigned the letter that their name starts with. And then I'm basically saying you will be related if this function assigns the same value. And this is one of the exercises in the problem set, proving that this is what I'm about to define. So this relation is special. Special. So why is this relation special? Because it satisfies three things that other relations need not satisfy. So the first one is for every student A, student B, and student C, just pick any three students, the following is always true. So A is always related to A, right? All of you have your name starts with the same letter as yourself. I mean, that's kind of obvious, right? From the way I define this. This property in general is called reflexivity. So this is a reflexive property. And a relation doesn't have to be reflexive. The one that I defined in the example above, the one I called R, this one is not reflexive because Alice is not related to Alice. Actually, no one is related to anyone. So that's that. I think that's called irreflexive. Is it called irreflexive? Anyway, I will write all these names down. There's so many definitions, and you don't need to memorize all these. But this one you do need. You do need to know what is the thing I'm defining right now. Okay, so another property that is very obvious in this particular example is that if A is related to B, then let's say Allison, Allison what? Okay. If A is related to B, then B is related to A. So if two people their names start with the same letter, then obviously the order in which I compare these two people doesn't matter, right? So that this property you might know is called symmetry. So you can reflect with respect to the symbol of relation. There's another property that's important that other relations need not satisfy. By the way, the relation R I defined up here in the example, this one is also not symmetric. Alice and Bob do satisfy the symmetry thing, but not Charlie, right? Alice is related to Charlie, but not in reverse. So this one is also not symmetric. And the last one is that if A is related to B, so if A and B start with the same letter, and B and C start with the same letter, well, then obviously the first person and the last person in this chain also start with the same letter, right? This is completely obvious in this example. It might not be obvious in other examples. So this is called transitivity. Uh, is this relation transitive in my example? What do you think? Okay, so some people are saying no. Okay, that's right. This relation is not transitive, but the counterexample is a bit weird, and there's something special about it, right? So Alice is related to Bob, and Bob is related to Alice, but Alice, the first person in the chain, and also Alice, the last person in the chain, are not related, right? So this is not transitive. Now, in this case, I used the fact that Alice and Bob have this symmetric relation to them, which begs the question, if you have symmetry sorry, if you have transitivity and symmetry, yeah, those are the ones I wanted, do you necessarily have reflexivity? Because if A is related to B and B is related to A, well, then you just apply transitivity to the symmetry and you get reflexivity, right? And this is what fails in this example, because in this example, Alice doesn't have a reflexive relationship with herself. So this is something that you should think about, and the answer will be given in today's tutorial. So actually, I managed to connect these ideas. Now, just a tiny spoiler, it's an interesting exercise to see why these properties are, let's say, mostly or completely independent, right? Why did I define three different things? Maybe two of them were enough to deduce the third one, and so there was no need for me to write three different properties. So let me write the important definition that will hopefully be repeated by the TAs during the tutorial. So a relation on A, and by the way, reflexivity only makes sense if the set on relations of the form A cross A, right? Subsets of A cross A. Because if you have completely different sets, well, then how are you going to relate something to itself if they are not in the same set? So this is important. A relation on A, so again, this is a subset of A cross A. It has to be the same set for this definition to make sense. Is an equivalence or an equivalence relation if it satisfies the three properties, the three above properties. So I just gave you the first example of an equivalence relation. Now let me explain intuitively what an equivalence relation is and why is it so special and so different from other types of relations. So here's an example. I will do this in green because this will be mostly like a discussion, rather than a concrete example. Let me move this thing out of the way. Again, feel free to interrupt me if you have any questions. Hope I'm still recording. Yeah, I think I am. Okay. So what's the thing about an equivalence relation? So imagine that this is the class of Mat 246. This is Mat 246. This could obviously be easily demonstrated if you were actually sitting in front of me rather than via Zoom, but I could make breakout rooms and achieve the same. Now, I will make a chunk here, a corner of the room, and I will tell everyone whose name starts with A needs to please cluster to this one. Okay, okay, I have a question is, why is the reflexive property false for the previous example? So in this example R, Alice is not related to Alice, right? There is no couple, no pair of the form Alice, comma, Alice. So this is not reflexive. And by the way, reflexive means not only that it's reflexive on the elements of R, but all the elements of A, right? So all students need to be related to themselves. And this doesn't happen in this case. Alice is not related. Actually, no one is related to themselves. So this relation is not reflexive. If I added the pair Alice, comma, Alice, then it would still not be reflexive because I'm missing Bob, comma, Bob, and Charlie, comma, Charlie, and so on. So here is an example. If I tell all of you whose name starts with the letter A to cluster into one corner, maybe I can then add everyone with the letter B, everyone with the letter C, and I do this for all the letters of the alphabet. What I'm doing is I'm partitioning the class, right? I'm partitioning. I'm not going to do all the others. I'm partitioning the class into groups. Now, this partition satisfies things that if I tried to define with a different relation, it would not work. I do need all three properties for this to be a proper partition. So for example, obviously, if I want to cut the group or cut a set into pieces, well, I don't want these pieces to overlap because then there's ambiguity, right, in the groups. If I wanted to evaluate you and make groups for you to work on an assignment based on the letter of your name, then obviously there shouldn't be an overlap because then some of you would get two different grades and that doesn't make any sense, right? So why is there no overlap here? If someone starts with the letter B and another person starts with the letter C, they can't possibly be in the same set. But could you prove this abstractly from the definition of an equivalence relation and not just in my example? So that's the first question that I want you to think about. Also, what other properties translate to this idea of a partition if you look at these three things that I defined or loosely defined within the example, right? Why is being reflexive important? Well, you can think about it this way. If a relation is reflexive, then everyone has a team because your team will at least contain yourself. So everyone will be in some team, and that's important, right? If I want to make teams based on this. Now, by the way, what if I want another criterion? Maybe I don't want the letter of your first name, sorry, the first letter of your name. Maybe I want to do something else. I want to make groups based on I don't know, based on height, a range of heights or based on the number of letters in your name, something like that. Which will define a proper partition and which ones will not. I already gave you an example of one that will not be a proper partition, right? This one will not work. And why will this one not work? Well, you can try to sketch it out and see why this one doesn't produce a nice drawing like the one I'm making here. We will prove this carefully and with more formality in the 2-hour Thursday lecture. But what I want you to think about is that equivalences are just a way for me to cut a set into pieces. But instead of defining explicitly what each piece consists of, I am giving you a rule and giving you the task of getting into the proper group, right? So here's the takeaway. Let me write this so that it's not just in the air. So the takeaway or the conclusion, takeaway. Okay, let's see if I have any questions. Okay, Nora's asking. Okay, so something I should maybe clarify. The word special simply means that this is an unusual or an extraordinary relation. The word special has no mathematical meaning here. So maybe I should change the wording a little bit. This relation satisfies the following. Satisfies that for every, yeah. The word special has no meaning, and as far as I remember, it will never be used in mathematical context in this course. Would be the same true if we flipped the if and then. Uh, okay, I think I answered the question, right? Yeah, special is yeah. Okay, perfect. Okay, so the takeaway from all this, and then we can end the lecture. The takeaway is that there are two ways of defining. There are two ways, at least two. Actually, if you look at the problem set, there's more than one, more than two. There's a third way in the problem set. If you look at the extra problems, there are two ways of defining a partition. I haven't told you what a partition is, of maybe producing a partition on a set. So I explicitly name the pieces. And two is I define an equivalence on them. This will make more sense next lecture when I prove that these two are the same thing. But the takeaway, just to put it into words one more time, if I want you to get into groups, then I can tell you individually what group you should belong to, right? I can say, okay, I'm going to create a group for the letter A. Then I'm going to create a group for the letter B, then one for the letter C. That will take a long time and it'll be a tedious process for me. Much easier is for me to tell you, get into groups with whoever students have the same letter as you. And then it's your responsibility to get into these groups. So instead of defining a partition by the individual chunks, in the individual pieces of the set, I can just define a relation and the equivalence will follow from this. We will formalize this on Thursday, so don't worry too much about this example. Just keep in mind that you need to know these three definitions for the tutorial. I will stay here for the next 2 minutes should you have any question for me. If not, you can also ask them on Piazza. Like I said, all the details are in the syllabus. Let me stop recording now. And yeah, it was nice meeting you.